Okay, thank you very much, Olaf. I'd like to thank the organizers for inviting me to this nice meeting. When I was emailed many months ago and asked to come here and give a talk, I felt very honored and privileged to be doing so on the occasion of Harold's birthday. So I've never collaborated with Harold, but around 18 years ago or so, we had sort of the same interests, and in fact, some of the work I did with Edwin fed into things that Harold was interested in. I think in the talk after mine, you're going to hear some of the history about the Gross-Wolkenhard model. So in searching for kind of anecdotes I have with Harold, I remember the first time I visited ESI. It was in 2008. It was my first time in Vienna. I was here for a few weeks on Harold's invitation, and I remember getting a phone call early on a Saturday morning in my hotel room, and it was Harold saying Satoshi Watamura was visiting as well. He said, "I'm taking Satoshi on a tour of Vienna. Would you like to join?" And I said, "Of course, I'd love to join." So my first vision of Vienna was thanks to Harold. So thank you very much for this lovely tour that we did on I think it was in December one morning. And the only other direct written collaboration I had with Harold is we co-edited a special issue for Sigma back in 2010 about non-commutative spaces, and I think there's several people in the audience who contributed to that special issue. But I thank you very much, Harold, for all the years of discussions and interactions, and I wish you all the best on your 80th birthday. Okay, so I'm going to go through it'll be clear why I chose this topic within the first 5 minutes or so. So let me just give an outline here. I'll start off with some general words of introduction and what is the particular problem I'm going to think about here. And then I'm going to introduce this framework for defining and studying what I call braided quantum field theory. And this is based on the homotopy algebraic approach to field theories, both in the classical case and in the non-commutative case. And what we have is a kind of braided version of that. And I'm going to explain what the braiding means in all this. So I'll tell you a bit about that. Then I want to go through the quantization of these theories. And the crucial thing is that we don't really do path integrals in this approach. We don't do canonical quantization. We use the BV formalism. And the BV formalism, modulo some functional analytic issues that I'm going to sweep under the rug, is a purely algebraic way of calculating the path integral. So that's what I'm going to try to sketch. And then I'm going to do this, I'm not going to do any examples until sort of the end, but I'll tell you about a non-commutative scalar field theory, what that looks like in this braided BV formalism, and how it's quantized. So this is a topic I've been working on for the last 3 years or so. It's with a long list of collaborators, not all on the same papers, different subsets of collaborators on different papers, but there's a list of them, and it's still work which is very much ongoing. Okay, so let's set the stage. This talk is about non-commutative field theory, and I think for a lot of people here, I don't have to motivate why non-commutative field theories are interesting. They appear not just in high-energy physics, they appear in many models as effective theories. Those of us interested in quantum gravity, we believe that these also provide some kind of a toy model for what quantum space-time might look like. There's a very, very famous and concrete example of where non-commutative field theories creep up, and that's in open string theory. So if you look at correlation functions in a constant Neville-Schwarz background field, in a certain low energy limit, these are the interactions between the fields are captured by the star product, Moyal-Bale star product, which I've written here in this form. Okay, so the way you read this is you expand the exponential as a formal power series in bidifferential operators acting on the respective tensor product, F and G, and then you multiply. The dot means the pointwise multiplication. So this led to a flurry of interest about 25 years ago. The constant B field case was generalized to both curved backgrounds and non-constant B fields, even possibly with flux, such as what Thomas was talking about earlier. And concrete examples of those are, of course, D-branes and Westhamino-Witten models, so with the target space as a Lie group. And more recently, the interest in these theories has been reinvigorated in looking at holographic duals to certain deformations of string sigma models. So I just bring this up to mention that, not to sort of try to feed string theory as the only application of this, but just to stress that even now, these models are very much of interest. Okay, so I'm going to work in this talk mostly with, well, exclusively with the Moyal-Bale twist. A lot of what I say later on will be true more generally. But the problem with non-commutative field theories with the Moyal-Bale star product is this famous, notorious UVIR mixing problem. So if we look at a scalar field theory, so these tildes mean the Fourier transforms of some scalar fields, the star product modifies the product in momentum space by these phase factors. Okay, and so if you have an endpoint interaction in scalar field theory, the interaction vertex will look like this. Okay, it'll have these phase factors. And the UVIR mixing problem comes up because there's now a distinction between planar and non-planar Feynman diagrams in perturbation theory. And the bad ones are these non-planar graphs, and they mix the scales. If you try to cut off a Feynman integral with an ultraviolet cutoff, it induces an effective infrared cutoff on the theory. Now, by itself, a non-planar diagram is not problematic. The problem is when you start inserting these graphs into higher graphs, and you start integrating over loop momenta. They start diverging uncontrollably because of this, and the theory cannot be renormalized. So why are these still of interest? Well, there's the famous Gross-Wolkenhar model. Okay, so this is, in general, you can consider phi-4 theory in 2D dimensions. So if you want to be concrete for renormalizability, you look at 2D equals 2 or 4. And you modify the kinetic term in the scalar action by adding a confining harmonic potential. Now, what Edwin and I showed before the Gross-Wolkenhar model is this gives you a kind of duality in the theory. So if you look at what the quantum field theory looks like in position space and momentum space, you find that up to some rescaling of parameters, the theories look the same. There's a duality under Fourier transformation. And this type of duality gets rid of UVIR mixing because now you have no distinction between what you mean by ultraviolet and infrared in the theory. And Harold and Reimar showed in a series of papers that was also supplemented by other works that that theory is renormalizable to all orders in lambda. Okay, so I'm not going to go and review any of that, but what I'm going to do is I'm going to take a new approach to renormalizable non-commutative field theory, where I'm going to keep the classical action the same, but I'm going to modify the path integral. And that's what I'm going to call braided quantum field theory. What we're going to find in this example of phi-4 theory is that there's no UVIR mixing, at least at one loop in the two-point function. And this suggests that the renormalization properties of this theory are very different. So UVIR mixing seems to be far less severe, and it may even be absent. We, of course, don't have a proof of that, but it looks like it may be absent. And the results we obtain are reminiscent of old works that came out around the early to mid-2000s, where people were proposing to modify the way you quantize non-commutative field theories by using notions such as braided statistics and that. So we'll find agreement with those results, but we're going to come to them in a much different way. Okay, these papers did not use any homotopical techniques. And in my opinion, I found that these works were a little bit ad hoc. The proposals were not systematic. The way we're going to quantize it is a systematic approach. Okay, so as I mentioned at the beginning, the way braided quantum field theory will work is we're going to rely on the well-known fact that any perturbative classical field theory is organized by something called an L-infinity algebra. And I'll explain that in a few minutes. And so what we'll do is we're going to deform this L-infinity algebra description to construct these braided field theories. And this is going to be done using the twist formalism. So we're going to have a Hopf algebra that's acting on the fields. And this theory is going to be equivariant with respect to that Hopf algebra action. It's going to be a triangular Hopf algebra. I don't know how to deal with the quasi-triangular case. This is not new. This was not, the notion of this kind of braided symmetries did not first appear in our paper. Some earlier work by Brzezinski and Majid already looked at this. And in fact, the community that was working some time ago on twisted non-commutative gravity really used these type of notions. So we borrow a lot of techniques that appeared there. Our work is most closely related to some work around 1999 by Robert Ockel, who wrote a paper called Braided Quantum Field Theory, but his approach is very different. It's a rigorous approach. It's again, doesn't rely on path integrals. It relies on developing a notion, an algebraic notion of Gaussian integration and a braided version of Wick's theorem. So we're going to come about that result from a different way. The drawback of Ockel's approach is he was only able to deal with theories that had no gauge symmetries. Our approach works for any theory, even with gauge symmetries. So what I want to do in the next 30 minutes is show you how the BV formalism, the Batalin-Vilkovisky formalism, can be used in a braided version, can be used to do calculations in these braided field theories. Of course, the BV formalism is not itself a modern treatment by any means, but when I say I'm going to apply this in the way that Costello and Guilliam did, Costello and Guilliam emphasized the algebraic aspects of the BV formalism. So that's very much the spirit of what I'm going to talk about today. Okay, so that's the introduction. Let's get on to some technicalities. So I'll just remind you about a couple of things first. The first is about a way to quantize any mathematical structure called the Drinfeld twist deformation formalism. So in the example, this is more general than what I'm stating here, but in the examples I'm looking at, I'm going to think of the Hopf algebra, which is the universal enveloping algebra of the Lie algebra of vector fields on some manifold. And then I define an object in the tensor product of that enveloping algebra called the Drinfeld twist. Okay, so this is some object there that satisfies a certain co-cycle condition. And just to keep things straight, I'm always going to work in this talk with the Moyal-Dale twist. Okay? But the formalism is more general. So when you quantize, if you have any module algebra, any representation, which is also an algebra for this Hopf algebra, for instance, functions, differential forms, tensors on your manifold, then the Lie algebra of vector fields and hence the enveloping algebra act via Lie derivatives on that algebra. So whatever operation we have on here, which I'll just generically write with a dot, we can deform it by letting the inverse of this twist act on the tensor product, and I'll call that a star product. So it'll define some kind of a non-commutative deformation of that algebra, and it carries a representation of the twisted Hopf algebra. So given the Drinfeld twist, you can define a new Hopf algebra structure. And I'm not going to need to go into details of that in this talk. Now the key is that if A is a commutative algebra, like the algebra functions, then the star product is no longer commutative. And I think mathematicians would say it's not even non-commutative, it's braided commutative or quasi-commutative, right? Because it's a controlled sense of non-commutativity. They don't commute, but you can control it with something called the R matrix, which in this case is just the square of the inverse of F. Okay, so I'm going to use this shorthand notation for the R matrix where I denote the corresponding legs in the tensor product like this. And again, it's a triangular R matrix, so it squares to the identity, and that's important for a lot of what I'm going to say. No, of B. So whenever you swap, it comes with an R matrix. And that's what the braiding is, okay? So in the original, before you deform, when you swap, you've just got the trivial transposition. There's no braiding, or the R matrix is just one tensor one. But now when you deform, you get a non-trivial R matrix, and every time you swap, so the transposition now is a braided transposition. Every time you swap, you have to accompany it with R matrices. Thomas. That's the formula for R. Well, it's an invertible element. It's a square of the inverse. It's F minus 1 times F minus 1. This is an element in the tensor product. It's invertible. So for the Moyal-Veil twist, you just change that to a plus to get F minus 1, right? Yes? Uh-huh. Yes, yes. That's because it's a co-cycle twist. I can, of course, do something more general with a cochain twist, and then I get an associator, and I get a quasi-Hopf algebra. And you can do that, but I'm not going to. Okay. So that's a reminder about the Drinfeld twist deformation formalism. Now, what are these L-infinity algebras? Well, a fact that has been known for many years to experts in the BV formalism, and which has been popularized more recently in some papers, is that L-infinity algebras organize the gauge symmetries and dynamics of classical field theories. So an L-infinity algebra is based on a Z-graded vector space, V, and the ingredients of your classical field theory fall into various graded components. So in degree 0, there's the gauge parameters of the theory, the things you use to act as gauge transformations. The physical fields of the theory live in the degree 1 component. The field equations are going to land in degree 2. And then the Nether identities, which are dual to the gauge parameters, are going to fall into the degree 3. By Nether identities here, I mean Nether's second theorem, not Nether's first theorem, which associates gauge symmetries with differential identities among the Euler-Lagrange derivatives of your theory. Okay, so that's what the vector space is, and it's equipped with a set of multilinear graded antisymmetric maps that act on n entries. Okay, and there's a set of relations that these satisfy. I'm not going to write them all out. The first few relations look as follows. The first one tells you that the first map, L1, squares to 0. So this vector space with L1 forms a cochain complex. The second relation is a type of Leibniz rule, so it tells you that L1 is a derivation of the L2 bracket. And then the third identity on the left-hand side is the combination you would write for the graded Jacobi identity. And it's violated in general, depending on the bracket structure of your field theory. Okay, so this is called a homotopy Jacobi identity because it's violated up to something depending on this cochain map L1. Okay, and then there's an infinite set in general of higher homotopy Jacobi identities. Okay, so these are the coherence relations of your L-infinity algebra. So, and I'll quickly flash how that's used in practice in field theories, but then the notion of braided L-infinity algebra, it's actually very simple. I don't consider this to be a very deep result. If you take a classical L-infinity algebra and you assume this is an L-infinity algebra in the representation category of your Hopf algebra, okay, so it means that all of the vector spaces are modules for the Hopf algebra, and the maps, these LNs I wrote, are equivariant. Then you can deform your maps, keep the spaces the same, deform the maps, and you get now an L-infinity algebra in the category of representations for this deformed Hopf algebra. Okay? And you just use the Drinfeld twist formalism. So the Ln star is just obtained by deforming these wedge products between the individual entries. Okay? It's simple. It's very simple. The axioms now change. So these are no longer graded antisymmetric. They're braided antisymmetric. So whenever you swap two entries, instead of getting a minus sign depending on the degree of the elements, you have to accompany it by these R matrices. And then you have a list of braided homotopy Jacobi identities, which I'm not going to write out. But again, the rule is always when you're writing down an identity and you start at one place, and anytime you swap two elements, you have to insert R matrices. So this is the effect of this braided deformation. Okay, so I didn't say it over here, but L-infinity algebra is a one-sentence word for what an L-infinity algebra is. It's a homotopy coherent generalization of the Lie algebra. And in a similar vein, braided L-infinity algebras are homotopy coherent generalizations of braided Lie algebras. So the notion of braided Lie algebra is, of course, not new, but this is a generalization of that concept. I also forgot to say here that we usually equip these L-infinity algebras with something called a cyclic structure, which is a non-degenerate inner product that has this cyclicity property written here. So this would be called a cyclic L-infinity algebra. And we can likewise deform the cyclic inner product, again, just using the principles of Drinfeld twist deformation. So how does this data capture field theories? Well, there's a prescription of how it works, which is based on something called the Maurer-Cartan theory of your L-infinity algebra. So the gauge transformations act according to the brackets on a physical field according to this formula, and the homotopy Jacobi identities guarantee that they form a braided Lie algebra under a braided deformation of the usual commutator of maps. The commutator, you take a product and then you subtract the flipped product, but now you put R matrices in there. That's what the braided commutator is. The field equations, the Euler-Lagrange equations of your theory are given by taking this infinite combination of brackets applied to your physical fields, setting that to 0 as the equations of motion, or more algebraically, they're the Maurer-Cartan equations for the homotopy algebra. Okay, and they're covariant. They transform covariantly under these gauge transformations. And then there are these braided versions of Nether identities. The first line in blue is the same as what, let me finish my sentence. The first line in blue is what you would get in the classical theory, And then the line in green comes really from this braided deformation. Yes, Thomas? Yeah, but that's what it is. This is the Maurer-Cartan equations have this covariance. And it's also when these gauge transformations of course close, they could be field dependent, right? So it's, and the cyclic structure comes in when you want to construct the action functional of the theory. So the action functional is given by this prescription, and indeed you can check that the variation of this action functional gives you back these equations, and also the gauge invariance of the action induces these Nether identities here. These Nether identities are identities. They hold off shell, and they follow from the homotopy Jacobi identity. So you can go and now take your favorite theory, apply this machine to it, and look at what the output is. And in many instances, involving theories with gauge symmetries, you get a theory that classically looks very new. And there are some surprises. Okay? And I'm not going to go through what the surprises are. I don't want to talk about gauge symmetries in this talk, but really what I want to do now is focus on how you would, this is all classical, how do you quantize this type of. And this is where the braided BV formalism. So you start with a braided L-infinity algebra with this cyclic structure. And so the BV formalism looks at observables, right? They looks at functionals of the fields. So we're going to look at polynomial observables. So we look at things that live in the symmetric, the braided symmetric algebra of this graded vector space. Okay, so I'm just going to denote the product of two elements in there as a juxtaposition. But you keep in mind that this is not commutative, but it's got this braiding in it, and also, of course, the usual grading factor. And there are all these kind of annoying degree shifts. That's what these square brackets around integers look like. I don't want to discuss those a lot. They're not so important. If you know what they are, you'll know why they're there. But that's basically the object we're looking at. Yes? It's triangular, yeah. Yeah. No. I know this is a bit of a misnomer. I completely agree. This is not really a braiding. So put differently, I'm looking at a representation category which is a symmetric monoidal category. And the more interesting thing is to look at a braided monoidal category, but I do not know how to do that. I don't even know how to define a Lie algebra in a general braided monoidal category. If somebody can explain that to me, then I'd love to hear about it. But yeah. So yeah, it's a bit of a misnomer, but calling this a symmetric quantum field theory sounds a bit weird. It doesn't sort of capture what we're trying to do, right? So, okay, so we're given this braided symmetric algebra, and now we can take our vector space V, tensor it with that braided symmetric algebra, and we get another braided L-infinity algebra structure. We change the differential on the L-infinity algebra by this formula. We change the binary bracket according to this formula here, and so on. Okay, and again, you see these R matrices coming in here. The R matrices here are because when I moved A2 out of the bracket, I had to bring it past V1. So that's where you get these R matrices. Okay, so this next few slides are going to be a bit technical, unfortunately, but what we'll do is we'll choose dual bases in my vector space and define these kind of contractions that in the industry they call contracted coordinate functions. And then I define something called the braided BV action functional. So it's given by this formula. This is S naught. This is the free part. And these are all the interactions. So this looks very much like this Maurer-Cartan action functional I wrote down earlier, but now it's done in this extended setting because the inner product is now valued inside this symmetric algebra. Okay, so this BV action satisfies a key identity called the classical master equation. And the bracket here is the BV anti-bracket. And it's defined in the following way. On generators of the symmetric algebra, so on elements that just live in this vector space, it's just given by the cyclic pairing between those two elements. And then you extend it as a braided graded derivation to the whole symmetric algebra in each of its slots. That's the way you define the anti-bracket. So that equation's important because what it tells you is if you define an operator Q by taking the original differential and then deforming it by the interactions in your theory, taking the anti-bracket, then that operator squares to 0. So it's also a differential. And so the classical observables of your theory are, as I said, the polynomial observables, polynomial functions on this space of fields, together with this differential and a compatible anti-bracket, and that forms something called the braided P0 algebra. So here are the axioms. The first is a compatibility condition between the differential and the bracket. The second is a braided symmetry identity. So this is not a Poisson bracket, but it's what they call a -1 shifted Poisson bracket because it doesn't have an anti-symmetry, it's a symmetry. Okay, and then there's a braided version of the Jacobi identity and also a braided Leibniz rule, something called a braided P0 algebra. Okay, so this is all classical. There's nothing quantum about this. How do we quantize in this formalism? So the key extra ingredient is something called the braided BV Laplacian. Okay, so this is a map on your symmetric algebra. It's defined in the following way. On the unit element in the symmetric algebra, it vanishes. On any element of V, any generator, it's 0. And if you evaluate it on the product of a pair of elements for V, you just take the anti-bracket. Now, this is not a derivation of the product on the symmetric algebra because there's a correction term depending on the anti-bracket. But using this formula, you can write down a general formula for the BV Laplacian acting on any string of elements in the symmetric algebra. So it's given by this formula here. And the point of this operator, what is it going to do? This is what's going to implement the braided version of Gaussian integration, or in other words, the braided version of Wick's theory. And the braiding, of course, will come from these R matrix factors. Okay, so the BV Laplacian satisfies some identities. And that guarantees that this new operator I defined by perturbing the old one with this delta BV is again a differential. So the quantum observables of the theory are now this pair, basically this differential complex, which is called a braided E0 algebra in this language. We lose the P0 algebra, this Poisson type algebra, because the derivation property here is violated. Okay, so these are the ingredients. And as I said, modulo functional analytic things, which I haven't addressed here, everything so far is very algebraic, right? And the path integral, the key thing in this formalism is how to compute the path integral. And that's given by something called braided homological perturbation theory. Okay, so let me spend a few minutes trying to explain what that is. So I'll explain all these ingredients. So this pair here is the original underlying cochain complex of your L-infinity algebra. And the L1 in practice is constructed from the free part of the theory. See that in a moment how that works. So this describes the free theory, and over here, because this is a cochain complex, I can take the cohomology of this cochain complex. And then, of course, the original differential restricts to 0 on the cohomology. And the thing you want to cook up to do the path integral is something called a strong deformation retract. Okay, so it means you've got some invariant map gamma here. You've got a type of projection from the vector space onto its cohomology, and you've got something which is like an inclusion of the cohomology back in. It isn't literally that, but in some examples it does turn out to be very simple. And so these maps have to satisfy a number of conditions that define what a deformation retract is. And in practice, this map gamma here is going to be given by the propagators in your field theory. So the significance of this is this defines a homotopy equivalence between these two cochain complexes. So you can now extend this to the observables by taking the symmetric algebra on either side. You extend these maps, have concrete formulas you can write down for how they extend. I'm not going to write them. But again, here you've got the propagators acting. And the key theorem, that's called the homological perturbation lemma, is that if you take this cochain complex and you perturb it by this thing I call delta here, so L1 star plus delta is just what I called QBV before, so this is the full interacting theory, then you get another strong deformation retract. And the maps which appear here have concrete formulas, which I'm not writing down, except for pi tilde. That's the one I'm going to use. And it's given by this formal inverse, which you can think of as a power series. Now, if you take a string of elements in V, you apply pi tilde, so that takes you from sim RV into sim R of the cohomology. The claim is that gives you the endpoint correlation functions of your theory. And they really depend on what the space looks like, because when you do perturbation theory, you have to pick a vacuum and expand around that vacuum. That's exactly what this formula is telling you. If there's a unique vacuum, this is trivial, and there's no choice, but in general, these are functions on this vector space of vacua of your field theory. So that's the key. This is the path integral right here. Okay, let me go back to the start of the talk, and let's apply this. So I'm not going to do gauge symmetries. And I mean, the BV formalism was really constructed to handle gauge symmetries, right? More general gauge symmetries, but it can be applied. It can be applied to theories without gauge symmetries equally well. And it still gives you a completely algebraic approach. Okay, so let's look at it. So there are no gauge symmetries. So I don't have the degree 0 and 3 component of my graded vector space anymore. I've just got the space V1 where the fields live, and the space V2 where the equations of motion are going to land, or in the BV formalism, it's usually called the space of anti-fields. But these are just both copies of the functions on R4, and I'm going to use the Moyal-Veil twist. What is L1? L1 is just the usual kinetic operator. So by box here, I really just mean the Laplacian. I'm working with an Euclidean signature. And I'm going to look at the example of phi-4 theory, which means setting all higher brackets to 0 except the third one. And that's given by this formula. Now this is a braided bracket. It's a braided L-infinity algebra because I told you at the beginning that if you swap any two entries in these star products, you get an R matrix factor. It's not an ordinary L-infinity algebra, it's a braided L-infinity algebra. But you apply the machine, you apply the Maurer-Cartan theory, you write down what the equations of motion look like. So that corresponds to setting this to 0, and that's just the usual equations of motion of non-commutative phi-4 theory. You can define a cyclic inner product just by integration, and then work out what the Maurer-Cartan action functional is, and you find this formula. This is just at the classical level, standard non-commutative phi-4 theory. So the statement is that the standard non-commutative scalar theory is organized by a braided L-infinity algebra. So classically, no difference, but the quantum theory will change. Okay? So just a fixed notation, I said before that when I was developing the BV formalism, that I had to choose a basis of field. So here I'm just going to use the usual plane waves, which pair to these Dirac delta distributions. Okay, so let's just see what everything looks like now. So we go apply the machine that I wrote down before. You compute this interaction action. You find that it's given by this formula here, where these V's are just these phase factors, essentially, that I had in the beginning of the talk. So the interactions are just what you would expect. The key thing is here is I'm not extracting them from Feynman rules. I don't have Feynman rules in this theory because I don't know what the path integral is. But I'm using this algebraic prescription to calculate what these interactions are. So no big shock there. We go look at the deformation retract that I wrote down before. I'm in Euclidean signature, so the zero modes of this operator when the mass is non-zero are trivial, so the cohomology vanishes. And the deformation retract looks like this, where this map here that I called gamma before is minus the usual propagator. Okay, now I apply this to observables. I take the sim of this thing here. So on this side, I have the sim. I perturb the differential by the interactions. On this side, because the cohomology is trivial, the sim of 0 is just C. So this map pi tilde is always going to give me just some number. And then the endpoint correlation functions are given by this formula, where these deltas are just, for now, just these delta functions. You could do something a little nicer and smear these out by not using these point delta function sources. That's a formula. And this is, you see, this is perturbation theory here. Okay? This term here is creating the vertices in your Feynman diagram expansion. And the delta BV with gamma are inserting propagators, and it's contracting lines together to give you the internal and external lines and graphs. So this is a power series in this coupling lambda, which I forgot to write here, and this constant h bar. Okay, this is braided quantum field theory, and so my last slide, I just want to quote what you find when you do these calculations. This is completely computable. Okay, you have to sit down and crank out some calculations, but it's certainly computable. And we've done lots of calculations. So the first example, let's look at the free braided scalar field. So turn off the interactions. Then the 4-point function would be given by this formula here. And then you could just use the explicit expressions in these rules to show that it has this expression in terms of 2-point functions. So these 2-point functions are the usual propagators of the scalar field theory. And that's just the braided Wick theorem, right? So you see that you've got this deformation here when you've swapped phi 2 and phi 3. There is a priori also a R matrices here because you've swapped things, but there's an identity which tells you that they go away. Second example, let's look at the 2-point function at 1 loop order. So put the interactions back on. So we're going to compute this quantity here. And you turn the crank, you do some careful calculations, you've got phases coming in all over the place, and you find this result here. The phase factors all just go away, and this is just the usual self-energy of ordinary phi-4 theory. So there's no UVIR mixing in this correlation function at this order. But I'll just mention, we've looked at many other theories, models of QED and other scalar theories. And in all calculations that we've done so far, we find similar quantitative results. This theory seems to get rid of all the non-planar graphs and keeps only the planar ones. That's the result new UV-IR mixing, and we're currently investigating to what extent does that persist at higher orders and in more